Okay, let's solve 21 the second way, and the second way is going to involve applying the Heaviside function first. So let's do that. What I want to do is first manipulate R a little bit before I start doing the Laplace transform, because what I have to do is incorporate the Heaviside into the R itself. To do that in this case is pretty easy. It's a sine of t, and then I'm going to multiply it by something. I can't multiply it by the Heaviside function itself, because this is the opposite of what it normally does. The Heaviside function starts at 0, and then at pi it switches to 1. And of course, I want the function to exist up until pi and switch to 0 afterwards. So here's what we do. 1 minus the Heaviside function at pi, and that'll take care of it. Because the Heaviside function is 0 until it reaches pi, it doesn't mess with this at all. It just allows it to be 8 sine t. And then the minute we reach pi, the Heaviside function switches to 1, and 1 minus 1 is 0, so it switches the function off and produces 0. Kind of brilliant, right? Okay, let's expand it. So it's 8 sine of t minus Heaviside at pi of 8 sine of t. The reason why I expanded it is we're about to do the Laplace transform, and the Laplace transform of this is very different than the Laplace transform of this. Okay, now we want to form capital R, which again is going to go in our algebraic expression. So I want the Laplace transform of 8 sine of t, and then minus the Laplace transform of the Heaviside function at pi times 8 sine of t. Well, earlier in the Heaviside video, I actually showed you how to do this Laplace transform. It's basically, we've got the Laplace transform of 8 sine of t, and then this guy just ends up producing an e to the negative pi s as a coefficient. So it's minus e to the negative pi s. And then it's the Laplace transform of this guy shifted by pi. So it's 8 sine of t plus pi. And that's it. This will be, if I do the Laplace transform of these two guys, I'll get R, the Laplace transform of the pair. And this is where the Heaviside function introduces some complexity. It's the idea that this is going to go inside the algebraic expression, and I've got this term for e to the pi s. But that's all right. Later on, we're going to be able to undo it, because in addition to the Laplace transform of a Heaviside product giving you this e to the pi s, at the end we get to undo it too, because recall that the inverse Laplace transform of anything that looks like this, e to the negative cs times the Laplace transform of some standard function, and remember that that guy ends up being equal to the Heaviside function at c times the original function f at t minus c. So it's just shifted by pi. So whenever I undo it, this is just going to reproduce the Heaviside function in my solution. So while it looks pretty terrible now, I'm going to easily be able to handle this term later when it comes time to taking the inverse Laplace, right? It just looks bad to work with, okay? Okay, first thing I want to do before I do the Laplace transform of these is take care of this. There's a trig identity that handles angle sum, and basically the sine of an angle sum at pi is just going to produce negative sine t. So let me just change that right here. Again, it's just a trig identity, and it gets rid of that part of it, so it doesn't turn out to be an angle sum, because I don't have a Laplace transform for an angle sum. All right, okay. Well, now we're ready to actually form our R. So our R is going to be equal to Laplace transform of 8 sine t is 8 over s squared plus 1. And then it'll be plus e to the negative pi s times 8 divided by s squared plus 1. So literally this whole thing is just 8 over s squared plus 1 times 1 plus e to the negative pi s. So that's our R. And now it's time to build our Y. So our Y is the same as it was before. Again, from the previous video, we already solved down to this point. So I'm just going to jump right to that. It was 4 plus this guy, 8 over s squared plus 1 times 1 plus e to the negative pi s, and then the whole thing was over s squared plus 9. And I'm actually going to expand this guy out again because there's a whole part of this that doesn't have the pi s, and there's another part that does, and we want to separate it into the two. The first part's the same as it was before. It's 4s squared plus 12, and that's over s squared plus 9, s squared plus 1, and that's identical to what we had before when we solved basically the top half of this separately. And then next to that we've got plus 8 e to the negative pi s, and that's all over the same denominator, s squared plus 9 and s squared plus 1. Once again, I don't really want to get bogged down with partial fraction decomposition. You can ignore the e to the pi s, just hold it off to the side when you do the partial fraction decomposition, and then it'll return to the numerator for each term in that, but it doesn't influence the way you do partial fraction decomposition. So let me cut right to the chase. This guy ends up giving you, when we're all done, same as we got before for this one, 1 over s squared plus 1, plus 3 over s squared plus 9. And then this guy, when you do partial fraction decomposition on it, ends up giving you 1 over s squared plus 1, and it'll be minus 1 over s squared plus 9. And then keep in mind that both of these have the e to the negative pi s times them, okay? Okay, so that's it. Now we're ready to sort of undo our partial fractions. And to do that, we'll use this on the second two, and we'll just use standard technique on the first two. So y of t is going to be equal to sine of t, and then plus this will be sine of 3t. All this guy does is brings in the Heaviside function. So this will be u at pi times whatever these functions turn into. And the only change is when I apply the inverse Laplace to anything that involves a Heaviside function, I need to shift it by the Heaviside value downward. So both these are going to be pi shifted downward. So the first one's going to be sine of t. So it's going to be sine of t minus pi. And then this guy's going to be 1/3. Oh, and it's minus 1/3. Again, the 3 on top will make it a sine 3t. So 1/3 sine of 3 t minus pi. And then that's it. Now that's the same solution we had before. It just isn't as easily recognizable. One thing you'll notice is some of these, the signs in front are wrong. This one's supposed to be plus instead of minus because we actually wanted to add it on. But don't worry, the trig identity is going to take care of that. When I apply sine of 3t minus pi, all it does is changes the sign of this term to make it sine of 3t. And the same thing here. It changes the sign of this one, so it'll make it the negative sign that I needed to cancel this guy out. So you notice this method produced the exact same solution as we got before. In this case, because the two initial functions that were part of R were easy, I think doing the separate analysis and then joining them at the end was easier. But there'll be times when these are difficult to work with on their own, and then it's just a question of whether you want to solve two complex problems or you want to do one complex problem, in which case this is a better way to go. All right?